Okay, so last time we talked about how to do Bayesian reasoning. We went over an example. Today we're going to do another example. In this segment, I should say, we're going to do another example. So suppose 10% of people in the population use a steroid. This is another of the examples that was on the homework that you were supposed to have done. So I should say, if you didn't do that before you watch this. If you use the steroid, then the test says you use this steroid 80% of the time. If you don't use the steroid, then the test says you don't use the steroid 70% of the time. So you can think of this here, if you've heard of talk of false positives and false negatives. When it says if you use the steroid, then the test says you use the steroid 80% of the time, that means it has a 20% false negative rate. It fails to catch 20% of users. And when it says if you don't use the steroid, then the test says you don't use the steroid 70% of the time, that means it has a 30% false positive rate. So 30% of the time it'll say you're a user even if you're not. Suppose 1,000 people take the test. How many of them are going to be users? Well, for the 900 who don't use, remember 10% of people use, which means in a population of 1,000, we're assuming it's representative, then 900 are not users. So how many of those 900 are going to test positive? Well, we then ask for the 100 who are users, how many of them will test positive? And then we find the total number of positives. And then we compare that total number of positives to the number of positive tests that come from users to give us the odds that someone is a user if that person is tested positive. So let's now go through and do that. So so we're supposing 1,000 people take the test. How many of them are going to be users? It's going to be 10% of 1,000, which is 100. For the 900 who aren't users, how many are going to test positive? Well, of those 900, the test is going to get 70% right, which means it's going to get 30% wrong. So it's going to say 270 of them aren't users, even though they are. For the 100 who use, how many is it going to catch? Well, we have our 100 users. It gets 80% of them right, which means it catches 80 people. It misses 20% of them. It misses 20 of them. How many total positive tests? Well, for the 900 who don't use, we get 270 positive tests. For the 100 who do use, we get 80 positive tests. So we add those together to get the total number of positive tests. That's 270 plus 80, which is 350. So how many people are actually using that test positive? 80. How many total people test positive? 350. So the odds that you're a user, given that you've tested positive, are 80 out of 350, which is around 23%. Remember, in this context, we're using this symbol for approximately, even though when we do logic, we'll use it for not. Okay, so if you didn't understand that, you can go back and look at the other videos to try and get on board, and you can go through this one again step by step to try and get on board. Here's another example. I think this one's helpful because I'll put the sort of relevant evidence right in front of the face of the person we're thinking about. So this is Mrs. 90%. And she's 90% accurate in judging color. And we're going to suppose that she judges a particular cab to be green. What are the odds that the cab is green? Well, we're going to suppose that she sees 10 cabs in a particular night. And 9 of them are blue, and here are those 9 blue cabs. And here's a simple question. How many of these blue cabs are she, for how many of these blue cabs is she going to say it's actually green? Well, she gets 90% right, so probably she'll get 1 wrong. And let's just say she gets 1 wrong. Well, one of those 10 cabs is green because 90% of the cabs are blue and 10% are green. And here's the green one. How many of these green cabs will she say are green? Well, she gets 90% of the color right 90% of the time. So for any particular one, the odds are she's going to get it right. So we'll say she says this one is green. So how many total times does she say green? 2. How many are actually green? 1. What are the odds she's right if she says the cab is green? 50%. So she's 90% accurate, but the odds that it's green if she says it's green are only 50% because most of the cabs that are in the town are blue. You can do this by deploying Bayes' theorem. You would take the probability that the cab is, you want to know the probability that it's green given that she says it's green, and you would take the probability that she'll say it's green given that it is green. That's 90% because she's 90% accurate. You'd multiply that by the probability of it being green independent of her saying anything, and to find the probability of it being green independent of her saying anything, you just see how many blue ones there are and how many green ones there are. Well, only 10% are green, so that's going to be 10%. Then what you want to calculate is the odds that she's going to say the word green. Well, she's going to say green 18% of the time. She's going to say it for this one green one, and she's going to say it for one of these blue ones. So that's 2 out of 10, which is roughly 20%. And once we stick the 90% times the 10% and divide by the 18%, we get 50%. So the odds that she's going to say it's green, the odds that it is green, given that she says it's green, is 50%. Okay, so we're going to continue now by talking about how to protect yourself from making the base rate fallacy in cases like this. First, whenever you have information about a test result and the accuracy of a test, refrain from drawing a conclusion until you can integrate that information with the base rates. So if someone tells you, and I can't emphasize this enough because people are so tempted to not do this. If someone tells you that you tested positive on a test that's 90% accurate, you should not draw any conclusion about the probability that you have the thing the test was testing for. Nothing at all. It tells you nothing. If only 1 in a trillion people have this thing, then the odds are very low that you have it, even though you tested positive, unless the test is perfectly accurate. If like 80% of people have this thing, then even if the test is only 60% accurate, the odds are pretty good that you have it if you test positive. So until you get information about the base rate, until you get information about the background frequency, about the prior probability, don't make a judgment based on some evidence that you're looking at right now. Don't make the judgment based on the accuracy of a test. What do you do when you can't find the base rate? That's a big question. One school of thought says just assign a base rate of 50% because that's kind of perfect neutrality. That school of thought is very controversial, and we'll talk much more about it when we get to the portion of the course on scientific reasoning. But we're going to stop our unit on thinking about numbers there, and we'll proceed next time by starting to learn about logic.